Alright, hey AP Chemistry. So this is going to be a video on bond energies, and all of that information is found in section 9.10. So in this video we're going to talk about how we could calculate bond energies using Lewis structures, and we actually talked a bit about this in the thermochemistry/thermodynamics unit. You may recall there was like a question where I gave you like bonds and you had to figure out the total energy, and it was some bonds broken minus bonds formed. We're going to talk about that in here and revisit that, because this shows up on pages 411 to 414 in your textbook. Alright, so here are some average single and multiple bond energies, and this is in units of kilojoules per mole. So for example, the way that you're reading this chart is an HH bond has 436 kilojoules per mole, a CH bond has 413 kilojoules per mole. Alright, so it says write the balance equation for the combustion of 1 mole of ethane, C2H6, forming H2O and CO2. Okay, so here is how you write this equation. C2H6, and I'm going to use gas, plus O2 yields CO2 gas, this is a gas also, plus H2O, and I'm going to make this a liquid. Okay, now if I balance this and I only want 1 mole of C2H6, just trust that it's going to look something like this, right? So it's going to be 7 halves O2 and 2 CO2 and 3 H2O. Okay, now if you have any questions about how did I balance it like this, that could be asked in a later or another time, but just know that we had to balance this chemical equation, and I kind of use a shortcut where you kind of use like 7 half O2, which gives me 7 oxygens on the left, and now I have 7 oxygens on the right. But we're going to use this equation because this gives me 1 mole of C2H6. If I were to fully balance this equation, I would try and get rid of this 7 half, and I would multiply the whole thing by 2, but I don't want that because I just want 1 mole of C2H6. So we're going to use this equation for this handout. Now this handout is not printed out for you, but it will be found in the Google Docs that were shared on the Google Classroom. If I want to draw some structural formulas involved in this chemical equation, C2H6 would look like this. All single bonds. Okay. O2 actually is a double bond with lone pairs. CO2, as mentioned in the quick check, looks like this. And then H2O, mentioned in an earlier handout, H2O looks like this. Okay? Alright, now we want to calculate bond energies of the reactants and bond energies of the products. So we have to be careful because each bond has its own bond energy, and that's kind of like a potential energy. It's energy that is stored, okay? A chemical bond is kind of a stored energy. So if I look at this, calculate the bond energies of the reactants. So CH, there are 1, 2, 3, 4, 5, 6 CH bonds. Each CH bond is 413 kilojoules per mole. So in total, if I want to get how much energy I have for all 6 of my CH bonds, I'm going to do 413 times 6. And I get 2478 kilojoules per mole for C2H6 value, right? I have 1 CC bond. Okay, so for my 1 CC bond, CC has a bond energy of, you see it right here, oops, sorry. CC has a bond energy of 346. So I'm going to put that there. There's 1 of them, so I'm just going to have 346 kilojoules per mole. And then O double bond O. O double bond O is my O2 molecule, that's a reactant. O double bond O, if I find it right here, multiple bonds, O double bond O and O2 is 498 kilojoules per mole. So 1 of them, 498 in kilojoules per mole, and I have 498 kilojoules per mole. And if I want the total energy of all the reactants, I add all of these together. So 2478 plus 346 plus 498. 3322 kilojoules per mole of reactant, okay? All right. Now I want to look at my products here, right? I want to calculate the bond energy of the products. Now it says C double bond O. There are two C double bond O's. One C double bond O this way, one C double bond O that way. Each C double bond O is, oh look, it has different energies here. C double bond O by itself is 732, but C double bond O in CO2 is 799. And so if I do them times 2 times 799, and I get 1598. Okay. And then OH for my water. Now, I have two OHs. Okay. I have an OH here, and I have an OH here. Okay. And so I'm going to have to take my OH, I find that up here, O and H has a bond energy of 463, kind of like HH, 463. And there are two OHs, be careful, OH over here and OH over here, just like there was a CO over here and a CO over here. And each OH is 463. So I'm going to do my 2 times 463, and I get 926 kilojoules per mole. Okay, but now we have to be careful here, okay, because I was doing some quick math and I had to realize something. There was one C2H6, but for my oxygens I have 7 half O2s. Okay, so I actually have to fix this number. This 498 corresponds to 7 half O2s, right? So whatever that number, that's 7 half moles of O2. So I'm actually gonna have to do 7 halves times my 498. So let me fix that over here. I'm gonna do the same thing over here. 7 divided by 2 times 498, that's 1743. So 1743. And I'm gonna recalculate this number. So I made this mistake on purpose, so I was just calculating the bond energies. I was just showing you where they are, but now I'm saying, all right, I want the bond energies of my reaction here, okay? So I have 7 half O2s, and if I do that, that gives me 1743. And so now I'm gonna do 1743 plus 346 plus 413. And I get, oh, I did wrong numbers. Sorry, 1743 plus 346 plus 2478. Now this is going to be all of the energy of the reactants involved in this reaction. 4, 5, 6, 7. 1743, 346, 2478. Right? This is all of the energy of the reactants involved in this reaction. My 1 mole of C2H6 has these 6 CHs and 1 CCs. My 7 half moles of O2 is going to have 7 half O2s, so 7 half of the 498. I'm going to apply the same thing over here, except I already got all the bond energies over here. I'm going to just have to fix these numbers. How many CO2s do I have? Well, from my balanced chemical equation, I have 2 CO2s. So if I draw another one, right, I'm going to have to take this number and multiply it times 2, because this number is for each CO, but there's 4 COs. So I'm going to have to do 2 times 799, or just take this number and multiply it times 2. So 1598 times 2, 3196 kilojoules per mole for all of the CO2s, right? So basically what I did was, here was my energy of 1 CO2, but I have 2 CO2s, so I had to multiply that by 2. I'm going to do the same thing for water. There are 3 H2Os. Here is my energy for 1 H2O. If I multiply it by 3, I'll get my energy for 3 H2Os. So 926 times 3 equals 2778 kilojoules per mole. Okay? And so now I'm going to have all of my energies involved in my products in this reaction. I just got to add these two. So 3196 plus 2778. That's going to be equal to 5974 kilojoules per mole. Now, if I want delta H of the reaction, and your textbook talks about this, it's going to be equal to the bond energy of the reactants minus the bond energy of the products. What is the delta H of combustion based on the bond energies? So my bond energy of the reactant, so delta H of the combustion, is going to be equal to bond energy of the reactants minus the bond energy of the products. And I'm going to use the numbers that I have here. I have 4, 5, 6, 7 kilojoules per mole. That was my bond energy of all of my reactants. That's my 1 mole of C2H6 and my 7/2 moles of O2. And then I'm going to use my bond energy of my products. That's my 2 CO2s and my 3 H2Os. So that was my 5974 kilojoules per mole. And if I do this subtraction, I'll have 4, 5, 6, 7 minus 5974, and I get negative 1400 or 1407 kilojoules per mole. Okay? So, we have done something like this before, where if I have all of the bonds in my structures, I look at all of the bonds that I have in my reactants, and I look at all of the bonds that I have in my products, and I have to subtract those energies. Basically, what this is saying is bond energy of the reactants is bonds that are bonds that are broken minus the bonds that are formed. And that is how we calculate bond energy, or the energy of the reaction according to bond energy, using bond energies. So this delta H of the reaction, or the delta H in combustion, I use solely the broken bond energies of the reactants minus the bond energies of the products. Okay? In part 2 of this video, I'm going to talk about how we could connect this type of calculation to using Hess's law that we use in thermochemistry.